While studying the phenomena called viscosity, we need to understand that we model the flow of the fluid in a different manner compared to the streamlined flow. So this modeling is called as the laminar flow. So lamina means a sheet, a two-dimensional sheet. So here I have drawn many lamina on top of each other. So these are the sheets of liquid, so as to say, and the liquid is going to flow in sheet wise manner or laminar manner. Okay, so what does that mean? What it means is, let us say this is a lamina, then this lamina will move towards the right hand side as the liquid is flowing from left to right. This lamina will move, and maybe it will move slightly lesser than the topmost lamina. Now why this happens, we'll understand that with an analogy. The most important thing to realize over here is we are modeling the flow of the liquid as if sheets of liquid are moving on top of each other. This is what we have to do while we study viscosity. So I have drawn an equivalent diagram over here wherein a stack of books has been kept on top of each other. We know from day-to-day intuition that if I give a shove or a push to this stack of books from the leftward direction towards the rightward direction, and I push all of them equally, okay, so it's not that I am preferentially pushing a certain particular book. I like all the subjects equally, so I am giving them all a shove from the left hand side, and that shove is an equal force or an impulse, if you will, that we have imparted from the left hand side to these books. Now this particular set of books will move like so. So this is what will happen. The topmost book will move the maximum. The simple reason for the fact is the topmost book has a force of mg acting on it. So because of that, the normal reaction N1 that acts on the topmost book is going to be equal to mg only. Similarly, the normal reaction that is acting on the second book is going to be kind of 2 mg, you can say, because on this surface 2 mg effective weight or force of gravity is acting because of the top two books. Similarly, on this third surface, we can say that 3 mg would be the normal reaction acting. On this fourth surface, we can say 4 mg would be the normal reaction acting. So as we are moving below and reaching the layers that are beneath, we can see that the books are moving lesser and lesser towards the right hand side. This is because of the increased normal reaction. The resistive force of friction that will resist the motion of these books is also going to be more for the books that are towards the bottom side compared to the books that are towards the top side. So I am trying to draw the resistive force of friction over here. So the resistive force of friction will be more for the bottom layers and it will be less for the top layers essentially. So this is something that is to be understood. Now when a liquid is flowing in laminar manner, the viscous force that will oppose the flow of the liquid is also similar and akin to this friction force that we have seen over here. So the viscous force is going to be effectively larger towards the bottom side and effectively smaller towards the top side because of the varying normal reactions. So viscous force, in other words, can also be said to be the force of fluid friction. Alright, now what we need to understand as far as the viscous force is concerned is the fact that different layers of fluid are moving with different velocities. So if I were to draw the velocity of, let us say, this second layer, let us say the velocity of the second layer is v, then the velocity of the first layer or the layer above it is likely to be v plus dv. So it would have a slightly greater or larger amount of velocity. This layer would have a velocity v minus dv. Alright. So let us analyze the top two layers. The distance between the top two layers happens to be, let's say, dx. Alright. Then according to the empirical law of viscous force, we can write down the viscous force Fv to be equal to eta. Eta happens to be the coefficient of viscosity. A. A happens to be the area of contact. So this area, the area of contact between the two layers. dV by dx. dV by dx, this quantity is known to be the velocity gradient. So this quantity is called as the velocity gradient. Velocity gradient essentially tells us how the velocity is changing as the height is changing, or as we move along the perpendicular direction, how does the velocity change? Direction perpendicular to the fluid flow direction. Alright. A happens to be the area of contact, that is understood. And this eta, okay, this is a Greek alphabet, eta. Eta happens to be the coefficient of viscosity. Much like the coefficient of friction, eta will try to reduce or restrict the relative motion between surfaces in contact. So here the surfaces in contact are the laminas of the fluid that are in contact. So eta is nothing but the coefficient of viscosity. Alright. Now this is the analysis that we performed currently, and we understand that this is the velocity pattern. The topmost layer is going to move with a greater velocity, the second layer will move with a slightly lesser velocity, the third layer will move with even lesser velocity, and so on. Alright, till we reach the bottommost layer is going to move with even lesser velocity. So whatever I have drawn and shown over here, we can say are the velocity vectors. The topmost layer is going to move with a greater velocity than the second layer, then the third layer will have even lesser velocity. So the way in which velocity is changing with respect to height is called as the velocity gradient. Now let's look at this diagram. Here we have represented a pipe. So this is the pipe in which a fluid is flowing. Now if this viscous fluid is flowing in the pipe, the central part of the fluid is going to move fastest compared to the edges. So this is a three-dimensional pipe. So towards the edge, the fluid is going to stick to the surface of the pipe more. Okay, and the central part of the fluid is going to flow faster, or the central part of the fluid is going to flow more. So this is how the velocity profile looks like when a fluid is flowing inside a pipe. Alright, here we have something called as the Poiseuille's equation for fluid flow. So we can write down, so let us say here the pressure is P1, and towards the right hand side of the pipe, let us say the pressure is P2. So we can write down the rate at which fluid is flowing. So d volume upon dt, the rate at which the volume of the fluid is flowing from left hand side to the right hand side. This can be written down to be delta P. Delta P happens to be P1 minus P2. Delta P upon 8 eta L. L happens to be the length of the pipe. Okay, so this is the length L, we can say. So this is 8 eta L upon pi r raised to 4. R is the radius of the pipe. So let us say this is R, the radius of the pipe. So we are talking about a pipe with a circular cross section. So it has a radius capital R, And this quantity right over here, this quantity can be said to be the resistance to fluid flow. So if we analyze this equation and actually compare it with the equation of current flow, which is namely dq by dt is equal to delta V divided by R, we can see that this is the resistance to the flow of current, R is the resistance to the flow of current.